Hello everyone, this is the demonstration video of the project that has recently been selected for the tape out in open source MPW5 shuttle program sponsored by Google and eFabulous. The project is basically the design of system on chip whose top level block diagram is shown in front of you. The core of this SoC is a RISC-V CPU, which is a 3-stage pipeline processor. It uses the Wishbone bus interface to connect with memories and peripherals. The CPU is programmable using an external SPI flash. This is done by the bootloader, which is resided into the boot memory. It is triggered out of reset such that the CPU loads the executable program from external SPI flash and store it into the instruction memory. When this process is finished, the CPU starts executing the instructions from the instruction memory. Now among the peripherals, we have UART, SPI and motor control. This motor control module is a bit special one as it is used to control the speed of the motor. It takes input from the quadrature encoder of the DC motor and generate PWM signal such that the desired speed of the motor is maintained in case it is altered by the change in the external voltage. Now we will see the working of this SoC for the motor control peripheral. Here is our complete setup. We have compiled the high-level program of motor control into RISC-V machine code and dumped it into the instruction memory of the SoC. Then the Nexus A7 FPGA board is programmed with the bit stream of the SoC. We have the DC motor along with the quadrature encoder. There is a circuit which consists of the L298 motor driver and the octocouplers. Then we have the variable DC power supply to vary the speed of the motor by changing its input voltage. An oscilloscope is used to observe two signals. One is the quadrature encoder pulses, which basically represents the speed of the motor, and the other is the PWM signal generated by the SoC. And UART to USB converter is used to display the messages on the computer terminal which are generated by the SoC. So the way it works is that the CPU on our FPGA takes quadrature pulses and set a reference speed of the motor by tuning the PWM signal. And when the input voltage of the motor changes to change its speed, the CPU adjusts the duty cycle of the PWM so that the reference speed of the motor remains intact. Now here is our motor controller in action. There is a putty window on the left side of the screen which shows the messages from the SoC via UART. On the oscilloscope, we have the quadrature pulses in yellow color and the blue waveform is the PWM signal generated by the CPU on our FPGA. At the moment, the speed of the motor set by the CPU is 10 units, for which the frequency of quadrature pulses is 5 kHz. Also 5 volts are applied to the motor, and in order to maintain the quadrature pulses at 5 kHz, the duty cycle of the PWM signal is set to 76%. Now we will increase the voltage and see that the duty cycle of the PWM signal will decrease to maintain the frequency of the quadrature pulses at 5 kHz. As you can see from the screen, if we increase the voltage up to 6 volts, the duty cycle of the PWM reduces to 58%. If we further increase the voltage to 7 volts, the duty cycle reduces to 46%. Also note that the frequency of the quadrature pulses remains constant at 5 kHz for the reference speed of 10 units. At 8 volts, the duty cycle reduces to 38%. On further increasing the voltage up to 9 volts, the duty cycle reduces to 33%. And finally, if we increase the voltage up to 10 volts, the duty cycle reduces to 29%. Now we will double the reference speed of our motor. When I press the H key from the keyboard, an interrupt service routine is invoked inside the SoC and a new reference speed of the motor is set at 20 units. Note that the input voltage is 10 volts, which is same as before. The frequency of the quadrature pulses increases to 10 kHz, which is twice the previous one. And the duty cycle of the PWM is increased to 45% in order to maintain the new reference speed. Now once again, we will vary the input voltage of the DC motor to see if the new reference speed of the motor or the frequency of the quadrature pulses is maintained or not. Note that on decreasing the voltage from 10 volts to 7 volts, The duty cycle of the PWM increases to 73% and new reference speed remains intact. This was all about the project demonstration. For the source code or the project documentation, visit the following GitHub repository.